shall discuss a classic example of motional EMF. But before that, just a brief recap of what is motional EMF. Let us consider we are having a frame which is like a U frame, like this. This is a U frame, and on which you are having a conducting rod. Okay, let this be A and let this be B. And let us assume that we are having a magnetic field which is into the plane of the board. And now in this scenario, I am moving the rod AB to the right. Okay, and let us assume that this is at a given instant, this distance is x and length of the rod is L. So now, if I happen to move this rod to the right, what would happen? So I would try to correlate at this point both in terms of left hand rule as well as right hand rule. Okay, so for example, there is a conducting rod, so it would have charge carriers. Okay, normally for flow of current we have electrons, but we consider flow of current as flow of positive charge, so I would consider positive charge. Okay, so now when I am moving the rod to the right, so I can assume that the positive charge carriers are there inside this rod. Okay, now these are being moved to the right. Okay, and it is the situation where the magnetic field is into the plane of the board. So now these charge carriers, which are positive charges, would experience force. Using Fleming's left hand rule, I can say what is the direction. Okay, so now if this is my hand and this is my forefinger, it must be representing the magnetic field direction. This middle finger must be representing the direction in which positive charges are moved, and this thumb would represent the direction in which these positive charges would experience force. So as the rod is being moved to the right, so along with the rod, these positive charges are also being moved to the right. So I would say my middle finger must be in the direction of right, and my forefinger, as you can see, is into the board because I have given cross, which is the magnetic field is into the plane of the board. So the thumb is pointing up. So I would rather say that all these positive charges inside this conductor would be experiencing a force in the upward direction. So I can say that the positive charges would experience a force in the upward direction, so that all the positive charges accumulate at the upper end. Now coming to the negative charge, it would exactly be the opposite. That means the negative charges would experience force to the downward side. That means the negative charges would accumulate at the bottom end. For now, let us only assume that this frame is non-conducting. Okay, for easiness of understanding, let us assume that this frame is non-conducting. Okay, so now what is happening is all the positive charges accumulate to the upper side of the rod and all the negative charges accumulate to the bottom side of the rod. So that now after some time you have the situation where it becomes like this, all the positive here and all the negative here. So is it not like a battery which is having positive on one side and negative on the other side? So it behaves as a battery, and obviously it has a potential difference between these two ends. Let us say the potential difference is E. Okay, so now this EMF is nothing but the motional EMF, and it has been generated because we have moved the rod to the right. Okay, so now if I want to get an expression for this EMF, I should say E is equal to d phi by dt, and here the phi, which is normally the product of the magnetic field and the area, here the area is the area of the loop, so it is BA. And as the area at a given instant, assuming we have said already that this is X and this was L. Okay, so now it becomes d by dt of B into Lx. So it becomes B L into dx by dt, which is BLV. So I said that the motional EMF developed must be equal to BLV. Okay, in other words, more is the velocity of the rod with which we are moving, more is the EMF developed across the ends of this rod, which is AB. For understanding further, let us now assume that this frame is conducting. Okay, now the frame is conducting. So what would happen? This positive charge and this negative charge would have got a path to flow. Okay, that means positive charge would be flowing in this direction and obviously negative charge will be flowing in the opposite direction, but we since take the current as the flow of positive charge, so I would say the current is flowing in this anti-clockwise direction through this frame. So I would say the current is flowing like this, like this, like this, and finally I would say the current is flowing like this. So finally I would say that the current is flowing in the rod from B to A. So now let us now correlate this happening with Fleming's right hand rule. So the Fleming's right hand rule gives the direction of induced current. So when a rod is being moved in a magnetic field, then what would happen? The current is induced in the rod. So the direction of induced current can be given by the right hand rule. Okay, now this time I would take my right hand with the same three fingers, forefinger, middle finger and the thumb. But this time my thumb is the direction in which I am moving the rod, and still the same, that is the forefinger is the magnetic field. Then the middle finger would be the direction of the induced current. So now going by this same example, now I was having the situation where the rod was being moved in the rightward direction. So I would put my thumb in this direction and magnetic field is still inward. So putting like this, I have got like this. That means what should happen to the flow of current? It would be upwards, right? So now as you can see, the current which was flowing in anti-clockwise has entered the rod in upward direction. You can see, okay? So the thumb is the direction in which the force on the rod was acting. The forefinger is inward because it is cross, magnetic field is into the plane of the board, and the middle finger is upward, indicating that the induced current is in the upward direction. So if I assume that it was a battery making a closed circuit, okay, so now the positive was accumulated at the top and the negative was accumulated at the bottom, and the positive charge was flowing into the loop like this. That means the current flowing like this, and while coming into this rod, the current is flowing from B to A, so which was nothing but the induced current. So I would rather suggest that any student who would try to understand this kind of concept should understand both in terms of Fleming's left hand rule as well as right hand rule. Left hand rule to be used for the accumulation of positive or negative charge on either sides for the rod to become a battery or source of EMF, and right hand rule then to correlate it with the flow of current, which is the induced current. So now let us go into the application for motional EMF. Now let us consider the application of motional EMF where we are having a conducting wire with capacitor in between in the form of AB. Okay, so AB is a conducting wire with capacitor of capacitance C in between, and it can, let us assume, slide over two rails. It can slide over two rails, two parallel rails, which are PQ and RS. Okay, and let the length of this wire from A to B be smaller. It is indicated here. Now let us also assume that mass of this arrangement of wire from A to B is m, as its length is L, mass is m. And now let us assume that it is this whole arrangement is vertical. The magnetic field is into the plane of the board and the whole arrangement is vertical. Okay, so that we can assume that the gravity force mg would be acting downwards. Okay, so now as it is going down, it is like we can now consider the concept of motional EMF. Induced current will be produced, okay, and in the process the capacitor would get charged. So in this scenario, we have to find, these are the things we have to find in this application. That means what is the actual acceleration going with effective acceleration downwards, and second thing is velocity as a function of time, and displacement also as a function of time, displacement of the wire AB as a function of time, and lastly the charge accumulated on the capacitor as a function of displacement y. Okay, so now let us start. From where to start? So if I take the three-point diagram equation for this wire, I would say this is the wire and its weight is acting downwards, mg. And now what about the induced current? So now it's going down. Okay, so I would use directly the Fleming's right hand rule. Okay, the direction of force, which is indicated by thumb, should be downwards. Magnetic field is inwards, so I would say like this. Okay, so now the induced current is in this direction, right? So if it is the induced current direction, what must be the force on this wire? Because we are having a force on a current carrying conductor in a magnetic field. Okay, so for that we can use the Fleming's left hand rule. Okay, so now if you are having the current flowing in this direction, middle finger direction, and the magnetic field is inwards, I am having the thumb acting upwards. Okay, so now what is the direction of force? It is upwards, so that it would be against the weight force. Okay, and the formula we will consider, what is it? Bil sine theta, BIL sine theta, and here theta is 90. The magnetic field and the length of the conductor are at right angles, so I will say it is Bil sine 90, which is Bil, BIL. So I have already mentioned here the force acting upwards is Bil, the force on the current carrying conductor. So there is a net force acting on the conductor which is downwards, and let us assume that the net acceleration downwards is A. So I can write mg minus BIL is equal to ma, where m is the mass of the wire. Okay, so now coming to, let us say this is equation 1. Let us say this is equation 1. So now coming to the induced EMF, as we know, it is BLV. Actually we have BLV sine theta also, here theta is 90, so BLV. Okay, so now BLV, now B is the magnetic field, L is the length, V is the velocity. So charge on the rod, charge on the capacitor would be Q is equal to C into E, because the EMF developed between the two ends would now try to charge the capacitor. So the charge on the capacitor would be Q is equal to CE, so it becomes C into BLV. So finally I would say Q is equal to CBL into V. So now quite obviously the current I can get as a rate of flow of charge. So the current would be dq by dt, that means d by dt of C B L V, except velocity. The remaining all are constants, so bringing them out, so it becomes CBL into dV by dt. It is nothing but the current becoming CBL into A. Here A is the acceleration, as I mentioned here, A is the acceleration with which it is moving. Okay, so I got the current the induced current expressed in terms of the acceleration as I is equal to CBL into A. Okay, so now this current I can now use in this first expression so that I can solve it further. So now we have just now got the current expression, and this was the already derived expression which was FBD equation. So now let us substitute and we can get an expression for the acceleration, which was what was one of the points which was to be answered. So now mg minus b into CBL A into L is equal to ma. So mg is equal to C B square L square A plus ma. So taking common, so I would have an expression for acceleration now, which is A is equal to mg by C B square L square plus m. So this would be the expression for the acceleration with which the rod is descending down. So we have answered the first part of the question. So now whatever we have been getting, I have been summarizing here. So now let us continue for the next part of the question, where he has asked to get an expression for velocity of this AB as function of time. So it is simply v is equal to u plus at, and starting from rest I assume, so v is equal to 80. So the velocity becomes v is equal to 80, implies v is equal to mgt by c b square L square plus m. So this becomes the expression for velocity of the wire AB as a function of time. So we have answered the second part of the question. So now I want to get also the displacement as a function of time. Again, assuming the displacement which with the starting velocity of the rod as 0, initially at rest. So as we have s is equal to half at square, and in the question he has mentioned the displacement symbol is y. So I would also take s as y. So it becomes y is equal to half acceleration I have got here. So it is mg by c b square L square plus m into t square. So this becomes the equation for displacement of the wire as a function of time. Okay, so we have also got an expression for y, and lastly we have to get the charge as a function of y, charge on the capacitor as a function of y. For that, let us first also write an expression for t. From the same equation we can just rearrange the terms so that we get expression for t. So time t becomes root of 2y c d square L square plus m by mg. So I can use this expression directly in order to get the last part of the question. Okay, so from the displacement as a function of t, I have got this expression for t. Okay, now to get the charge on the capacitor, because it's getting charged, so charge on the capacitor as a function of y. So let us again consider the expression we got at the beginning, which is for the current. Okay, so now I is equal to CBL into A. Okay, so now on one hand I can write I as dq by dt, and on the other hand I also have an expression for acceleration which also I can substitute. So it is dq by dt is equal to CBL into the acceleration we have got mg by c b square l square plus m. Okay, so now I think it should be clear now that as I want to get charge, I would take this term dt that side and I would integrate. So I got an expression for dq in terms of dt. Okay, so integrating both sides, I have integral dq is equal to cbl into mg by cb square l square plus m into integral dt. Okay, so I think it is clear that since all these terms are constants, nothing is variable, so I would bring them all outside the integration. So what is the only integration is for the time dt. So it is from charge 0 to q and this is for time 0 to t. So obviously this becomes q is equal to cbl into mg by cb square l square plus m. Okay, now it is time t and I have an expression for t here already, so I would substitute. So it becomes q is equal to cbl into mg by cb square l square plus m into the expression for t I would substitute, which is root of 2y into cb square l square plus m divided by mg. So that now I can make the relevant cancellations. So let me rub this part of the board so that I can do the rest part of the derivation. So now here it's very clear that mg is outside the root in the numerator and here it is inside. So one cancellation here will make this mg will be eliminated, but here it will be root mg, and the term here in bracket cb square l square plus m, and here also it's the same term, so that term will cancel and this will come inside the root. Okay, and 2y is as it is, so we would get like this. So mg into 2y by the denominator cb square l square plus n. So finally the charge q is cbl root of 2 mgy by cb square l square plus n. So we have now got the last part of the question where it was asked to obtain charge on the capacitor as a function of the displacement of the wire AB vertically, which was denoted by y. Thank you.